Good morning everybody. I welcome you to this session on transistors. Earlier vacuum triode and vacuum pentode were being used for amplification of signals, and later on the semiconductor transistor was developed. For instance, in 1946 Shockley and his team at Bell Laboratories were given a task of developing a small semiconductor device which can work as an amplifier, as a replacement for the vacuum triode. And within 1 or 2 years, that is in 1946, so a transistor was developed. And this was the greatest invention of this century. It has revolutionized the field of electronics, and because of which it paved a way for the integrated circuits which are available now. Now millions of transistors can be integrated onto a small semiconductor chip, and we have computers like the Pentium machines and digital signal processors available today. So this is one of the greatest inventions which have revolutionized electronics, the field of electronics. A transistor is a 3-terminal device. It can be made out of 2 p-type materials, semiconducting materials, and with an n-type material sandwiched in between, or 2 n-type materials sandwiching a p-type material between them. Okay, here an n-type material is sandwiched between 2 p-type materials, and here a p-type material is sandwiched between 2 n-type materials. So here it becomes a PNP transistor, and this is an NPN transistor. So we make ohmic contacts for the p-type, this n-type and this p-type material. So, and by convention we call one as the emitter. So this terminal, this middle terminal, as the base, and this terminal as the collector. Emitter, base and collector. So it has 3 terminals. With 3 terminals you can have 2 independent ports. The between emitter and the base can be an input, can be used as an input terminal, and emitter and collector can be used as an output terminal, or emitter and base can be used as an input terminal, base to collector can be taken as an output terminal, and so on. Okay, this way a few combinations of 2 independent ports is possible, and these independent ports act as, these 2 independent ports act as an input port and an output port. So to the input we give one signal, and at the output you get the output signal. So between the output and the input, an amplifier works like as an amplifier amplifies the input and gives as the output, and a transistor can be used for amplification purposes. Now a transistor can have current, emitter current, base current, and the collector current. By convention we take the current going inside as the positive. IE is the current going inside. If IE is equal to minus 1 milliampere, means IE is 1 milliampere actually coming out of the terminal, and IE is plus 1 milliampere means the IE is equal to 1 milliampere going inside the terminal, emitter terminal. and the symbol used for this is like this. The circuit symbol used. So this is emitter, this is base, and this is collector. And to indicate that this is a PNP transistor, so an arrow is used here to indicate that. So an inside going arrow indicates the direction of the current at the emitter, that is inside. In a PNP transistor the current goes inside, IE is positive. So therefore the current direction is indicated here as in this direction. In an NPN transistor on the other hand, the current goes out of the emitter. Therefore, so this is the symbol used, indicating that the current goes out of the emitter. So naturally the emitter current is negative in this particular case, with IE as our emitter current as the current going inside. Since the current actually comes outside, it is negative emitter current. Now a transistor is formed by taking doped semiconductors. Usually the p-type, which acts as the emitter, is doped with high concentration, and the base has intermediate type of concentration, and the collector is usually with low concentration. Okay. So because of this difference, when you invert the terminals, I mean when you take the reflection of the terminals, that means using collector as the emitter and emitter as the collector, the characteristics usually differ, because these devices, these emitter side, collector side and base side doped semiconductors have different concentration level, which is maintained purposefully to give you high amplification. The purpose is to give you a high amplification. Usually this base material thickness is maintained very low, so that the transport phenomenon occurs in a transistor. We shall see what this transport phenomenon is and so on in the next lecture, in the subsequently. Now when the transistor is formed by considering a thin base and a highly doped N side, we have holes as the majority carriers here and electrons as the majority carriers here on the base side, and similar to the p-n junction, we have a p-n junction formed the moment these two materials are brought closer with clean surface. The holes diffuse into the base side and the electrons from the base side diffuse into the emitter side, and as a result of which you have negative charge accumulating here, the space charge accumulating here, and a positive space charge accumulating here. Because of the diffusion of the mobile charges, the immobile atoms are left with some charge, the opposite charge, and as a result you have the space charge developed across this. And this space charge further prevents diffusion of the holes into the N side over here, and this space charge on the emitter side prevents further diffusion of electrons from the N side into this P side. So you have therefore space charge of this type developed. Similarly, On this side of the junction also you have space charge developed. So now if you plot the potential, you will find that the potential is, ideally the potential is like this. For a positive charge, the force acting on the positive charge would be, which to drive away the positive charge away from that particular point, or the energy we have to spend in bringing a positive charge from infinity to this distance or to this point would be like this. Since it is accumulated positive charge, you have to do work to bring a positive charge from infinity to this place. Therefore, the potential is positive here. So this is the potential, where this is the p type, this is the n type here, and this is the p type side. This is the distance. And what about the charge carrier concentration? Well, we have minority carrier concentration like this. We have electrons on this side, holes on this side, and we have electrons on this side as the minority carriers. Well, if this device is connected in a circuit, the minority carriers can be drifted from the p side to the n side, and from n side to the p side, and so on, if the circuit is complete, and some external potential is applied to this. So when nothing is connected, this is the state of affairs. So because of the space charge, you have the potential of this type developed. Now, if we apply some, let me use the same diagram. Now, if we apply a small positive charge, apply a small positive potential to the emitter base junction, that means in the PN junction convention, if we forward bias the emitter to base junction and reverse bias the base to collector junction, what happens? Let us examine what happens in this situation. When this junction is forward biased, naturally this potential difference between the p side and n side is reduced by the external potential. So this potential barrier is reduced by elevating the potential of this p side with respect to the n side, and because of that there will be huge amount of diffusion, a large amount of diffusion of holes from the p side to the n side that takes place, and the diffusion of electrons from n side to the p side that takes place, just similar to that of a semiconductor, similar to that in the case of a semiconductor or diode. Now this diffusion is, if you plot the concentration, diffusion concentration, so this diffusion is very large at this junction, both sides. Let us consider the whole diffusion. Whole diffusion is very large, and as the holes diffuse into the base side, so they do recombine with the electrons over here, the majority electrons over here, and some current flows through this side. Okay, naturally there would be current passing, so this side because of the diffusion, and part of it will definitely go across this because it recombines, the holes recombine with the electrons over here. But please note that the base region is very thin. as far as distance is concerned or dimensions are concerned, it is a very thin layer. So because of which, before appreciable amount of recombination that takes place, the holes are attracted by the potential difference over here, and they cross the base into the p side, into the collector p side. Why? Because you have the potential gradient of the opposite type here, and this p side is biased with a negative potential. As a result, the p side, this p side has a potential which is very lower than very low compared to that of the base, compared to the base potential. So because of this negative potential on the p side, so the holes which are injected into the base get accelerated or get drifted into the collector p side. So the diffused charge holes are drifted into the collector, a huge amount of it, maybe 98% of it, or 99% of it, or 95% of it. The diffused current passes to the collector. So it appears like some collector current in this direction. So this is what happens with the holes. And the electrons which are present here, so these electrons partially get recombined with the holes coming over here, and they contribute for some amount of base current which is going in this direction, which goes in this direction. And the electrons get diffused into the p side, and they contribute for some emitter current in the opposite direction. Now because of drift, it appears like a collector current over here. This is what happens when this junction is forward biased and this junction is reverse biased. And this injection of the holes into the base region or diffusion of these naturally depends on this forward potential here, this junction potential over here between the emitter to base junction. Any questions on this diffusion of the holes from the emitter side into the base and the drifting of these injected holes into the p side by the reverse potential applied across the base and the collector?
Sir, how does the low doping concentration help?
Pardon?
How does the low doping concentration help?
The low doping concentration helps in controlling in deciding the majority charged majority injection carriers. If you want the majority of the current as holes, so you should have high hole concentration here, and if you want the recombination of the electrons to be low here, you need low number of low concentration, low doping concentration for the base. Similarly, if you want to reduce the diffusion on this side, of course diffusion doesn't take place here. If you want the same hole current to be dominating, you should have low concentration on this side also. Plus if you want a huge potential drop here between the base side and the collector side, that means a large space charge region to drift the injected holes with high acceleration, you need to go for low doping concentration here. So when the doping concentration is low, the depletion region would be large and the potential difference would be large, and the transportation of the injected charge carriers into the collector would be better, because that is desirable for operating this device as an amplifier. We shall see, we shall discuss about it subsequently. It's clear? Any other question? Now let us look at the current components in this device. You have this is this side in this on this axis, it is the current magnitude and this is distance, and I am indicating currents over here. So due to holes, diffusion of holes, you have large amount of current, hole current, so that is passing in this direction. So this current is due to the holes from the emitter side. So let me indicate it as IPE. And due to diffusion of electrons from the base region into the emitter region, you have again here an emitter current, positive emitter current, and so that is, let me indicate it as INE. And naturally this current is much lower than this current because the doping concentration on the emitter side is much higher than that of the that on the base side. Because of this reason, this current is much larger than this current. So this current is because of electrons getting diffused from the base region into the emitter region. Now part of this goes out as base current, part of it is, and most part of it passes into this region as the collector current. So if I indicate this as IPC, and this is naturally IPE minus IPC, this part of it is. So this is what is with the diffused part of the charged particles, and this particular current is because of the diffusion from base side into the emitter side. Therefore this current also contributes for the base current because it is coming from the base region into the emitter region, and this current is drawn from the circuit, base side circuit. So this is about the emitter base junction. What about the base collector junction? The base collector junction is reverse biased, as you have seen in this diagram. It is reverse biased, and this reverse bias is good for the minority carriers, that is the electrons on the p side and the holes on the n side. For them it is a potential which drifts these charged particles. As a result, they get drifted in this direction. The electrons, the minority carrier electrons drift in this direction, and the holes drift in this direction, because of which there would be minority carrier current which is similar to that of a reverse biased PN junction current. Therefore you have here minority carrier current flowing like this, and this minority carrier current is of a low value, and this is partly due to the holes. If I indicate it as IPC naught, and the electrons, minority carrier holes and minority carrier electrons. So it is due to summation of the drift of these two, and this is, so this current naturally is between the reverse biased collector junction, collector to the P side here and then N side over here. Therefore, so this current also flows in this direction. Hence, this whole thing amounts to some current flowing in this direction. So, you expect IB to be some negative current. We expect IB to be some negative current. And these two put together constitutes these two put together makes the emitter current, which is positive because it goes inside, and these two put together makes the collector current, and which is this minus this, this minus this, and that is usually negative. So, these are the current components in a transistor. So, expressing the collector current, this IPC as, or the collector current as alpha times IE, because a fraction of this gets diverted into the base and most part of it goes into the collector. Therefore, this current IPC can be expressed as a fraction of IE, almost about say 98% of IE. So, alpha is here, alpha is of the order of about 0.98. So, we can definitely express, so this IPC as alpha times IE. And apart from IPC, you have this current here, which is due to the reverse biased PN junction. So, and that current can be expressed as IC naught into 1 minus e to the power of Vc by eta Vt. So, we know that in a PN junction, reverse biased PN junction, the current in the reverse direction is equal to, or in any direction, for the current is in general equal to IC naught into 1 minus e to the power of the voltage applied by eta Vt. This is the characteristics, the volt ampere characteristics of a PN junction. And now here we have this reverse biased PN junction. Therefore, the reverse current can be expressed as in this form, where the voltage applied is the collector to base potential Vc, or the collector junction potential. So, with this expression, for large Vc, we know that this is approximately equal to IC naught, this current is. Okay, so this is very small, as you know, it is very small, which is of the order of a few nanoamperes in the case of a silicon transistor and few microamperes in the case of a germanium transistor. Now, with this, the current, the collector current, expression for the collector current can be given in this fashion. So, it can be given as shown here. The collector current IC is equal to minus alpha IE plus IC naught into 1 minus e to the power of Vc by eta Vt, where IC naught is the reverse saturation current of this PN junction. And please note that this negative sign is coming because of the convention. So, here the current is positive, as I mentioned, and the collector current IC is the current which is coming inside, and since actual current is alpha times IE goes outside, therefore IC is equal to minus alpha into IE plus, so this current is current which goes inside here, as per the symbol IC naught is, because it is the reverse current, and because of that it is additive over here. Hence, so this is minus alpha E plus IC naught into 1 minus e to the power of Vc by eta Vt. So this is the expression for the current. As I mentioned, alpha is of the order of 0.98. Any questions? Now let us take up an important application of the transistor. A transistor works as an amplifier. Let us see how a transistor works as an amplifier. Now in this transistor which you have seen here, so this is a PNP transistor. We have forward biased the emitter junction and reverse biased the collector junction. Normally the forward potential is very small, of the order of about 0.6 volts, because it is a PN junction here. Therefore, it is indicated in this fashion, I mean as shown here, and on the reverse potential is usually high, which is typically 5 volts or 10 volts. So we apply a large reverse potential over here, and let us use a load here, load resistance RL. Now, if you apply a small alternating voltage here, after biasing the transistor like this, if I apply a small alternating signal over here in series with this bias and tap the voltage across the load resistance, we find that this is an amplified version of this voltage. So if this voltage is a small voltage of this type, let us say an audio signal of this type, on this side, so you will find that this is a large voltage signal of with the shape retained, but with the amplitude magnified. If this is say 10 millivolts, this may be 1 volt with an amplification of 100, with a gain of 100. So let us see now how this kind of amplification is possible. When you apply a small alternating potential over here in series with the supply, the forward potential on this PN junction changes according to this voltage. So the forward potential over here is VEB plus this voltage. If this voltage may be some small incremental voltage, a small maybe plus 10 millivolts or minus 10 millivolts of or something in between, say. So then the diffused current, or the current that diffuses from the emitter junction into the base junction, changes proportionately. Because this potential is being changed, this potential barrier is being changed by either it is increased or decreased based on this potential being positive or negative. So the current that is injected from the emitter into the base region changes. So and that current, so naturally is drifted into the collector, almost 98% of it is drifted into the collector, and as a result the collector current, also the current that is flowing in this direction, which is minus IC, also varies proportionately, and say, let us say, so this, oh I am sorry, this is millivolts, 10 millivolts. So this current is say contributing for a proportionate amount of so when you apply this voltage here, so let us say the emitter current, which is when this voltage is not there, say the emitter current is 5 milliamperes, say 98% of that 5 milliamperes goes to the collector and 2% of it goes out of the base. So that is the situation when this alternating potential is not introduced. When this alternating potential is introduced here, so we expect the voltage to change, and the changed voltage causes the emitter current to change because of the changed potential barrier here, and as a result say this current, which is 5 milliamperes, changes on the positive side up to 6 and on the negative side up to say 4 milliamperes in this fashion. Now this current is almost 98% of it, the collector current is, with a negative sign of course. Therefore the collector current also would be almost the same waveform with, so 98% of 6 and 98% of say 4 milliamperes, approximately 4 to 6 milliamperes. This is how it changes the collector current. Now if this resistance is of the order of 1 kilo ohm, what do you expect as what kind of voltage do you expect at the output over here? When this alternating signal is not present, we expect the 98% of this 5 milliamperes on this side. I am neglecting this current, the reverse saturation current, okay, in which case it is almost the 98% of the emitter current as the collector current, okay. So that is approximately 5 milliamperes, and dropping across this 1 kilo ohm resistance, you will find 5 volts at the output of RL. Now when this alternating component is introduced, we have this alternating component introduced into the collector current. So because of which, so the signal, the voltage which is 5 volts, which was 5 volts before applying this signal, will now go up to 6 volts to say 4 volts on the negative side and 6 volts on the positive side. So now what's happening? So apart from, in addition to the DC voltage here 5 volts, you have the alternating signal coming out, and the, what is the magnitude of the alternating signal? So it is plus or minus 1 volts. Whereas on this side, the, what is the amplitude of the alternating signal? It is maybe a few tens of millivolts. A few tens of millivolts is causing a large change in the diffusion current, and the diffusion current is getting transferred to the collector, and therefore the collector current variation is also of the same order as that of the emitter current variation. But when this collector current variation is dropped across a large resistance, you have a large amount of voltage that is appearing across the output. Well, does this varying voltage from minus 4 volts to 6 volts, this varying voltage, does it matter in the transportation? Well, earlier if the reverse potential is say 5 volts, it may vary from 4 volts to 6 volts, or if the reverse potential is 10 volts, because of an additional drop over here, so this may be slightly reduced to 9 volts, or it may be increased to 11 volts. When this voltage changes between 4 and 6 naturally, so this voltage also changes, because sum of these two is equal to this voltage. Now the question is, by allowing the alternating current to drop here and then cause a large amount of voltage variation, does that voltage variation have any effect on this alpha? If alpha also changes according to this signal, then we won't have proper amplification. But please note that in a reverse bias junction with large amount of voltage variations, irrespective of whether this voltage is 5 volts or 10 volts reverse voltage, there is the change in the current is very small. Therefore, the collector current to emitter current relationship doesn't vary much with the variation in the reverse. For this reason, we can afford to use a large resistance here. So see that this current drops across this resistance and gives you an amplified signal. So this is what is helping you in amplification. On this side, if you have a resistance, a large resistance, and see that this current drops across this resistance, here also you will get a large amount of voltage. But with a large resistance connected here, the most of this potential drops across this resistance and very small amount only gets dropped across the forward junction, and hence you will not get that current amplification. Because of this transport phenomenon here, we can afford to have a large voltage drop across this by connecting a large resistance over here. Okay, I'll further discuss about it in the next class.